Hello students, in this video lecture, we will study sampling theorem. The importance of digital signal in the field of communication and signal processing is well known. But the problem is that almost all the real world signals are continuous time signals. But to resolve this problem, what we do, we convert a continuous time signal into a digital signal, then process it or communicate it, and again at the receiver end, we convert the digital signal into a continuous time signal. Now, the process of converting a continuous time signal into a digital signal is having two steps. First is sampling, another is quantization. In sampling, what we do, we convert a continuous time signal into a discrete time signal. Discrete time signal is a signal which is continuous in amplitude but discrete in time. Okay? Then again this discrete time signal is converted into digital signal using quantizer. Okay, that digital signal is what, in which both time and amplitude are discrete. Okay, so we will focus over sampling process. Now when we convert a continuous time signal into a discrete time signal, we take some samples and we have a frequency of taking samples. But to reconstruct this discrete time signal at the receiver end, we have a restriction over sampling frequency. What is that restriction and how we will derive it? We will take an example and mathematically we will analyze it and then we will find out that what is that restriction. So let's see. This is a continuous signal xt. This is a baseband signal. Baseband signal means a signal which is having a finite range of frequency in which the value of signal is non-zero. It means this frequency, like we can understand it with the frequency representation of the same signal. Now this xt is represented into the frequency domain. Don't relate it, I have taken for an example. So suppose this is a frequency domain of a signal, of a continuous time signal, and here what you see, that the value or magnitude of x omega signal is present between only omega m and minus omega m and plus omega m. After that range there is no value of that signal, means it will contain a range of bandwidth. Okay, so these kind of signals are being converted into digital time signal, so discrete time signal. Okay, so now let's see xt. When we have taken this continuous signal and we have to convert into discrete time signal. So what we have done, we have multiplied it by function ct. You can see this is a discrete time function. Okay, this is a pulse train ct. Okay, so this function or this signal is multiplied with this. Let's see what will happen when we will multiply the value of 1, means the value of ct is 1 at these points, 0, minus ts, minus 2ts, and this is what, this is the sampling frequency, ts, sampling time interval. Okay, ts, 2ts, got it? So at t is equals to 0, look, only this value will be presented here, and between 0 to ts the value of ct is 0. And this ct, after multiplying the xt, it will also make the value between these two 0. Got it? So in this way, only at these instants the value of function will be appeared, and except these the value has become 0. These values we have got. So this signal, now this signal, look, this signal is converted into a discrete time signal. It is not continuous in time. Okay, so you can find out that at every point of time you cannot find the value of the signal. Now let's write its points also, like ts, 2ts and 3ts, here minus ts, minus 2ts, minus 3ts. Got it? So this is a very simple process. Now look at this. If this signal xt is multiplied with this signal ct, then we will get the sampling function, sampled function, okay, that is xt into ct. So this is what a sampler. It is a simple process, but we need to ensure that the sampled signal we have achieved here, that must be reconstructed at the receiver end. So there is some conditions for this signal to be reconstructed at the receiver end. Let's analyze them with mathematical analysis and then we will predict the condition. Okay, so let's start with the signal ST. This is sample signal. Sample signal ST is equals to XT into CT. Okay, let's take frequency domain. Means we will take Fourier transform of this function. Then S omega will become 1 by 2 pi. This, listen, that XT and CT, this is the multiplication, and multiplication will convert into convolution in frequency domain. So let's see, x of omega convolution C of omega, it will convert into x of omega convolution C of omega. Now see here, C omega is the Fourier transform of this function CT. Okay, now look at the function CT and we have to find out the Fourier transform of this function. Then C of omega will be equal to, sorry, C of omega, let's write it here. This is equation 1, and C of omega will be equal to 2 pi summation n is equals to minus infinity to plus infinity, and Cn, this Cn has nothing to do with that function C. Okay, this is different function. Del of omega minus n omega s, omega minus n omega s. Okay, now let's define this function C. This function Cn is equals to C of n omega s divided by C of n omega s divided by Ts. Okay, let's put it here. It will become 2 pi summation n is equals to minus infinity to plus infinity, then Cn is put as capital C n of omega s divided by Ts. Okay, C of n omega s divided by Ts, then del of omega minus n omega s. Now see that the value of C n omega s means at the integer values. Look here, integer value. What is the value of C? The value of C is 1. Okay, for all the values of C, integer values of t, the value of Ct is what? 1. So we can put it here 1. Okay, at the place of C of n omega s, we can put it here as 1. So we can write it 2 pi upon this Ts I have taken out. Okay, Ts summation n is equals to minus infinity to plus infinity. Okay, this has become 1, and inside what is left? Omega minus n omega s, and this quantity will become, now 2 pi by Ts is what? Angular frequency or angular sampling frequency. Okay, so this is represented by omega s. So omega s summation n is equals to minus infinity to infinity del of omega minus n omega s. Okay, so this value of C omega we will put in equation 1 and we will proceed further. Now we will write the equation number 1 after putting the value of C omega. Now S omega will be equal to 1 by 2 pi, and x of omega we will put as it is, x of omega convolution with what is the value? Omega s summation n is equals to minus infinity to plus infinity, and del of omega minus n omega s. Okay, so this is, now we will solve it further. Look at this. This x of omega is constant. Omega s is constant. Let's take this omega s outside and take this summation for the whole value. So now omega s, this omega s I have taken outside upon 2 pi. Okay, and this summation, we have taken this x of omega inside the summation because no n is there, so it will be a constant for this summation. So we can include this also in the summation. So we can write x of omega convolution, with del of omega minus n omega s. Okay. Now, by the property of unit impulse function, look at here, this is a unit impulse function. By the property of unit impulse function, we will solve it. So we have to understand that one property is there, xt. If xt is convolved with del of t minus t naught, then the answer is, the result is x of t minus t naught. Okay, it means that any function, if any function xt is convolved with a unit impulse function of t minus t naught, then this t will be replaced by t minus t naught. Look here, let's compare it with the expression and check what will happen to this. X of omega is convolved with del of omega minus n omega s. So this will result into x of, and in place of omega we will put this value omega minus n omega s, as in place of t we have put t minus t naught. In the same way, at the place of omega we will put omega minus n omega s, and we will write it as omega by 2 pi and omega s. This is omega s. So omega s upon 2 pi summation n is equals to minus infinity to plus infinity, and x of omega minus n omega s, x of omega minus n omega s. Okay, so in this way it is received. Now this omega s upon 2 pi will be converted into, omega s will be 2 pi upon ts. So it will become 2 pi upon 2 pi ts. 2 pi is cut by 2 pi, and this will remain as n is equals to minus infinity to infinity x of omega minus n omega s, or if I will remove it 2 pi, so we can convert it into 1 upon ts, because 2 pi is cancelled out, so 1 upon ts, and summation of n is equals to minus infinity to plus infinity x of omega minus n omega s. That is the frequency domain representation of this function. Okay, now what we have to do, we will represent it in the frequency domain. This s omega we will represent in frequency domain, and let's check that it is recoverable or not. First, pause the video and write all these steps. Now we will recover this. Now we will draw the frequency spectrum, okay, or Fourier transform frequency domain representation of this s omega. So we will find out this as, for n is equals to 0, suppose n is equals to 0, what will happen? This is s omega. At n is equals to 0, you will find out when we will put n is equals to 0, it will become x of omega. Okay. So at n is equals to 0, suppose this is n is equals to 0. So one function will represent that omega, x of omega, and x of omega is here. So minus omega m to plus omega m, and that 1 upon ts will change only its amplitude, nothing more will be changed. So it will come here like this, minus omega m to plus omega m. Okay, for n is equals to 1, this is for n is equals to 0. Okay, for n is equals to 1, what will happen? Omega minus omega s is t minus t naught, when the function, when the this is what time shift, it is being time delayed. Okay, so it will shift at the omega is equals to omega s, means the center point of this signal will shift to the point omega s. Okay, because it will become when we will put n is equals to 1, then x omega will be the result will be x of omega minus omega s. Okay, basically it will be a series. So I'm writing it here first. I think you may be confused. So ts in bracket, it will go to minus infinity, so I'm not including each and every term. So first is at n is equals to minus 1. So at n is equals to minus 1, it will become omega plus omega s. Okay, and plus at n is equals to, this is what, at n is equals to minus 1, and at n is equals to 0, it will become x of omega, and plus n is equals to 1, it will become x of omega minus omega s. Okay, if you will study time shift of a signal, then if a signal is subtracted by any constant time value, then the signal is shifted, is delayed to the same number, means this is being occurring at omega is equals to 0, this is occurring at omega is equals to 0, this center point, that center point will come at omega s. What does represent? X of omega minus omega s. Okay, so this function will be like this. And this point will be omega s minus omega m, and this point will be omega s plus omega m, and so on. आगे बढ़ता चला जाएगा, and in the negative x axis also there will be infinite number of these kind of signal in frequency domain. Okay, so here we can understand that this point you are looking omega s minus omega m, okay, and omega m, there is a gap. This gap is known as guard band. Now if this point is coming becomes less than, means if understand or suppose the condition where omega s minus omega m is less than omega m, means the point, this point will come here. Okay, it means that I will show you with an example. This diagram will become like this. This is omega m, and this is omega m minus s, omega minus omega s minus omega m. Okay, if omega s minus omega m is less than omega m, then this condition will occur. Okay, in this situation you can see that the signal has been distorted, that x omega is not recoverable, it has been distorted. Here one overlapping will occur, and due to this overlapping the signal cannot be recovered in its original form. Okay, for the sampling process one condition is there, that omega s minus omega m must be either greater or equal to omega m. Look at here, this is the same situation. Here look, you can see that omega s minus omega m is greater than omega m. Okay, so there is a sufficient space between them and we can easily recover the original signal from this converted signal. Got it? Now what we have to do, omega s minus omega m, we have got a condition that omega s minus omega m is greater than is equals to omega m. Okay, then we can say that omega s is greater than equal to 2 omega m. We have taken this omega here and we have find out the final condition, omega s must be greater than equal to 2 omega m. It shows that to recover a signal, we need sampling frequency such that omega s is always greater than equals to 2 omega m, where omega m is what? Maximum frequency contained in the massive signal, that is known as xt. Okay, so we can write the sampling theorem's statement. The statement of sampling theorem: a signal can be represented in its samples and can be recovered back when sampling frequency is greater or equal to twice of maximum frequency component present in the signal. Maximum frequency component present in the signal. If many frequency components are available in the signal, then we will take the maximum frequency signal of the massive signal. Okay, we will understand it with an example also. Now, Nyquist rate. We have studied that omega s is greater than equals to 2 omega m. Okay, if I talk about the minimum value of omega s for which the sample can be successfully converted into discrete time signal, now we will see that it will become omega s is equals to 2 omega m. Omega s is equals to 2 omega m. Okay, so the minimum value of sampling frequency must be must be equal to 2 omega m. Okay, and corresponding to this angular frequency omega s, the frequency means f of s must be equals to 2 f of m. F of s must be equals to 2 f of m, not from here, 2 f of m. So this frequency, sampling frequency, is the minimum sampling frequency that can be kept in the sampling process. So Nyquist rate is nothing but this frequency. We will study the minimum sampling rate omega s is equals to omega n, means minimum sampling rate is what? Omega s is equals to 2 omega n, or fs is equals to 2 fm required to recover the massive signal is known as Nyquist rate. Okay, and interval Ts corresponding to Nyquist rate is known as Nyquist interval. Got it? So what we have finally concluded that fs is equals to 2 fm. Okay, so this is what Nyquist criteria. It is also known as Nyquist criteria, and f of s is known as Nyquist rate. So we have taken a question. In this question, what is asked? Find out Nyquist rate for the function xt. This is a massive signal, and for this signal we have to find out Nyquist rate. Okay, so we will see. Let's see in this signal. There are two components of the signal. One is sine of 50 pi t and another is cos of 200 pi t. We will find out the frequency component of these. This is what? Omega. We can write it as omega 1. Okay, and this is known as omega 2. Okay, because the sinusoidal function is in a signal is kept as sine of omega t, okay, or cos of omega t. Got it? So this is what, after removing t, whatever is left is known as omega or angular frequency. Here also we have find out omega t. So which is greater? We can write it as omega 2 is greater than omega 1. Okay, so in this signal, what is the maximum frequency? Maximum frequency omega m is what? Omega 2. Okay, and omega 2 is 200 pi. Okay, corresponding to this, we will find out according to the Nyquist or sampling theorem. According to sampling theorem, we can write fs must be minimum sampling frequency must be equals to 2 f of m. Okay, and 2 f of m is written as basically omega is equals to 2 pi f. Okay, omega is equals to 2 pi f. So f will be omega upon 2 pi. So it will be omega m upon 2 pi. Got it? And 2 into omega m, the value of omega m is 200 pi divided by 2 pi. So pi cancel out, and this 2 is by 2, and the answer will be fs will be 200 hertz, and that will be your answer. Okay, in this way we can find out Nyquist rate. It is a very important question to find out Nyquist rate from your university examination to your competitive examination.